Thank you for the introduction and the organizer. Here, I will, of course, we have a very nice background from Kelly. I would make easier for me. We also introduce the windowless magnet-based spin trunking devices. Over here, we introduce about spin wall and also spin talks. And as in a few days, you already found that spin 2D magnet is very nice playground. Have a lot of physics, like you play with laser, play with strain, play with Murray, and some proximity effect. But this material actually has a pretty long discovery history. And you can date back to 1940s. This is a 2D easily model. And also this Murray Wagner model theorem, which shows that no order is possible. In this Heisenberg, means this one, a magnet is possible. But until very around 26 and 27, this and 2D Isling antiferromagnet and some ferromagnet were discovered. But just a few years later, many more materials come out, from insulating to metal materials, from ferromagnet and antiferromagnet. Today, I will show you some works on this iron germanium telluride. And this classical material is very unique. So when you increase atoms of iron, it shows the current temperature increase, and also saturation magnetization also increase. Of course, all these materials are metallic, which is important for the electrical spin injection or SOT stuff. So another one is you can take some position of iron with cobalt. You can this cobalt doping level. You have ferromagnet, antiferromagnet, even some spin textures here happened. It shows different structures, of course. So these have very good tunabilities, anisotropy, even further enhance the current temperature and different magnet orders, ferromagnet, antiferromagnet. So in 2022, we push the windowless magnet-based device to the room temperature, uses the FIGD with graphene. 3 years later, we have more devices working at the room temperatures with different combinations and anisotropies. So basically, here I will show you two classes functions devices. One is we're proving this magnet status with spin wall. And also, we try to do some SOT memory applications like this magnetic manipulation, like switching. First one, we use this lateral spin wall signals. Means we take advantage of this magnet and also this graphene interface, like windowless interface, to injecting or detecting the moments here, because the spins can go to the interface, then detecting by the reference contacts. So like this here, we can realize both inject spin from the FGT here, FIGD. Also, we can detecting by the spins from the cobalt. So there we can know the spin directions, and from the FGT, then we can roughly tell that it's same moment, magnet moments is still also there. So see here, we can that the spin wall signal, both injection and detection, should very good and robust operations. And basically, you apply the implant field, so that means we have very good implant spin polarizations. Also, our signal analysis show that it's very large spin polarization happen at the interface. FGT, and it is just use the windowless gap, no any other insulated barrier or something. So further, we want detecting what's the moments looks like in the FGT. So here we use the Handler precession method. There, like here, you apply out-plane busy field. You will process moments across the spin here, where from the moments. If here the moments is parallel to the field, it's no precession, basically the line here curve. If this moment is in plane along a copper direction or across any parallel is fine, you will see the symmetry curve. Otherwise, if it's anti-symmetry, like MX field, you will see the anti-symmetric curve. So here, we see the curve like here. Basically, we can see in this FGT, we see the X direction spin polarization, Y direction spin polarization. We can also try to use the BX. Then we can detecting the SY, correspondingly the MY, also a zeta and zeta here. Here we see very clear zeta spin polarization, but you see this Y spin polarization is very, very minimal. But here you can see we have already clearly SY, but here we do not see anything. That means when we apply the in-plane field, very likely we align the moment to the MY direction. That means the magnet at room temperature is pretty soft, at least at the in-plane. So that gives conclusion that in this material FGT, we have looks like canted FGT. But it looks like likely it's easy plane, it's in-plane, means XY plane, but there's still some out-plane canting. Very occasionally, we find some very special geometry like this, like string kind, so some enlarged one. We found some very unique spin signal. This is never seen before. So here we see the normal FGT. You're typically have two status, low and high. These are very typical ones. But here we also see another one. Like we have 4 status, 1, 2, 3, 4, 5. And here we define two components. One is SD, we call it single domain. Another one is spin texture here. I will explain it a little bit. The second part. So first one is easy. We mainly how to understand the second one. Means when there's a field, you can see both directions, similar. It's switching before 0, not after. So that means when field go to 0, this energy favorably is good to like anti-parallel. They're canceling each other or compensate each other, you can say. So here at the very beginning, we think it's kind of like anti-ferromagnet in the material, but we do not find any evidence for this material, some like oxidation or something. But later we found that there's some other literature that said in these FIG materials, it's a pretty relatively high DMI, which suggests some potential like spin textures can be there. So also, if there's some strain or some notch, you can lock these spin textures at the interface. So similarly, you can inject this relative spin textures into the graphene as well. So there we can see some spin textures from literature. We have some schematic here. It can be like this. So basically, they compensate each other. If the field is around 0, means when field is 0, it's like middle stats minus 0. But when you apply the larger field, you can align everything to the same direction. So you can go to the another low resistance sensors. So in this work, we show that it very possibly we have both normal single domain FGT. Also, we can observe some spin textures. They can coexist, but both are in the interface, at an interface. So, as I said earlier, if we take some iron with cobalt in doping, here for example 50% cobalt doped, we can say that our work show that this basically we got a very nice and strong in-plane anisotropy. Means here from the Hedges loop, you can see that it's like very like traditional ones, not like the one we see FGT. It's very weak. It can switch most around zero field. Here is a very large field. And also we only see SY components here, means this material have very good in-plane isotropy. And also we cooperated with a series group from Uppsala. They confirmed this by the DFT calculations. And further, we go to even higher cobalt doping, around 50% of the iron was doped. There we found even novel, some magnetic orders appear there, so make us possible to realize field-free, as we talk, applications, switching operations here. So first, let's see what the material looks like. Here we make a Horvath geometry with another signal. Here you see is outplane field. We see 3 stages, roughly, you can say. This is the benchmark signal with the antiferromagnet. But you may also see a small loop here around zero field range. So if we do very finer scanner here, you can see it has pretty like outer plane look like and magnetic anisotropy. So we even go further, we go to very small step sweep. We found that even some shift happened. This like suggests that looks like the antiferromagnet there, they can introduce exchange bias. So this effect presents all the temperatures, even to very low temperatures. Then we do a full temperature mapping with the different field and temperatures. So we found there's coexistent ferromagnet and ferromagnet. They present very high temperatures. With analysis, we show that this nil temperature could be around 400 K, and the current temperature ones around 360 K. And also, we do this another signal with out plane rotation to in plane, so we can do a very careful analysis to see that this magnet also some canting, not exactly to out planes. So with a very simple model, this is the easy axis here. So we can, according to the relation with the exchange bias and also the field, we can extract the canting angle around 10 degrees of canting away from the outer plane. So then we try to understand this material, why there's 2 different kind of magnetization moments happening here. A team group in Chalmers, they find that this is pretty uniform at the very first size. You can see the 4 elements most everywhere, and no special difference. But with a fine scan for each layer, they found that there's an eye, usually is an eye missing, like here. We can defect, which. But another thing is this: all the elements are symmetry along the germanium here. So this can only explain this. Look like we have a dominant antiferromagnet, of course, from this magnitude we said this is also dominant. But how to explain the another magnet orders? So there, after a very careful check, they found another case here. They found 2 symmetry vaccines in some area, some place, and these very likely they can correspond to the ferromagnetic components. And we take this information to the series group from Uppsala, and they try to build models taking different position of the ion, and with these 2 geometry, one is the anti-symmetry ion defects, one is the symmetry anti-defects. They found that most likely this second type is ferromagnet type, and the first one is antiferromagnet type. And also, they calculated the angle with Monte Carlo method. They said this canting angle around 80 degrees, which agree our experiment part pretty good. And they, after some calculations, they see that this canting is due to computation between this exchange bias with FM and FM, and also some magnetocrystalline anisotropy energy. both effects contribute to this canting. So with this information and knowledge, we can try to use this material for SOT and for the switching. So a little bit theory background on this, how this SOT works on the moments. So basically here, we can take a field instead of spin first. If a field is not perfectly aligned with the moment, the magnetization will be processed along with the field, but due to damping, the finally will align with the field. So this is called field torque. So similarly, if a spin working on the moment similarly we can rotate the spin direction. Finally, also align with the field spin direction. Also, so this kind we call field-like, means it's like a field torque. Second one, also another torque type called damping one, means you align the moment direction directly rotating to the spin direction. So typically in one material, the both are there. So that means the spin polarization can, one is the rotate, another one is the processing. So we're processing, rotating to the direction of spin direction. So this is how it works. So as Kelly has showed that us, if a magnet with PMA, means out plane, that is very preferred for the industry applications because it can have even very high information storage. But in this case, because this is perfect geometry symmetry, you apply the current here, like spin direction here, the moments will be processing and finally align this direction of the z-axis. So it will not go to another direction. So this is called non-determinate case. So you need additional field here further to process into the opposite direction. So this is typical limits. So this actually, for real applications, the external field is usually not preferred. So here in our geometry, we have a canted ones. This is the break the geometry symmetry. So if we have a spin direction working here, it's rotating just over this hard axis. Then it immediately go to next direction. So it does not need any further field. So this is a very good case. So now let's see how that works. Here we use PT as spin source. This is very available and very easy in the clean room as well. We deposit the PT on top of these materials and the micro bars. So we can apply the current here. But basically, we use pulse current because it can minimize the thermal effects. So we apply, if you scan this current direction, you can see we sweep from one direction moments downwards to the upwards. So then sweep back again. So it basically means you can use the current itself, can switch the magnetizations. So then we also try the field, of course. We want to see with the field how it works. And of course, we also see the switching everywhere. But it does not change the directions. According to the theory, if the field applied positive and negative one, it will change the switching direction from clockwise to anti-clockwise. But here you can see all the switching direction is the same. That means our switching is very robust against any external field up to at least 500 millitesla. So it's safe and with external disturb. And also, we check this robustness of the measurements. So here, we try to do from negative current to positive current and do many times writing. Then we measure the signals. So you can see with field, without field, and positive negative field, they're always very reliable to see this switching up and down, up and down. So we don't do many time. This can be 1,000, 10,000 or even more. So very robust. Then we use the harmonic measurements, means we have low frequency second harmonics to check the SOT efficiency. And we found that this is, of course, field-like torque, time-like torque, both are there. And found the spin work conductivity is pretty good, of course, compared to other field-free devices. Basically because we have PT, it's very strong SOC. Also, it has a very low resistance. So that means very conductive. So further, we want further to push this application to all 2D heat structures. We use the Ti tantalum inert telluride, which is like a tungsten telluride. It has geometry like this. So it has lower symmetry, only one mirror symmetry. The other one is not. So there, you can get like spin polarization. You apply current on A. You have both in-plane and out-plane spin polarizations. But in-plane B is like a normal metal. So you only have the in-planes. So also we measure here FG80. It's a show pretty good, nice square loop, which is a little bit different, but it's most 400K TC, very nice PMA. So this is the preferred. According to knowledge before, if the spin direction is outward plane, which parallel to the moment direction, you also don't need field assistance to further switching. So there you can see when we apply the current along A, there's no need field. We can do the field sweep, do the current induced switching. But along these high symmetry ones, it doesn't work. So after some analysis, we show that these all 2D materials devices, they have even lower power consumption and very high spin orbital efficiency. So in summary, we use different of anisotropy materials from FGT, this different cobalt double level materials, even some FG80, which is all these very high TC materials, high TC materials, which is good for the real room temperature applications. We realize the different functions like spin walls and electrical method to detecting spin textures, although some O2D very close real applications. And finally, I want to thank you, the audience, and also all the collaborators. And feel free to ask any questions. Thank you.